Ngày bên nhau em nói anh là người cuối cùng, cớ sao hôm nay thành hai chữ đã từng. ngày bên nhau.
Một nét số định trong nền kinh tế thị trường, định hướng xã hội chủ nghĩa ở nước ta hiện nay. Trong nền kinh tế thị trường, định hướng xã hội chủ nghĩa ở nước ta hiện nay. Đâu được coi là khả năng là bài đáp án gì hả lớp? Đáp án gì? Các bạn, đáp án gì? Đáp án gì? D, đúng rồi. Tại sao này, cô phân tích cho các em này. Tại sao lại là D? Là bởi vì nhá, chúng ta để ý câu hỏi có từ để hỏi. Câu hỏi có từ để hỏi đó là
Told you maybe even 6 months ago that that approach wasn't going to work that well. With some of the tips that you learned in this course, I hope that you'll be one of the ones to not waste those 6 months, but instead be able to make more systematic and better decisions about how to build practical working machine learning applications. So with that, let's dive in. In detail, this is what you see in the 4 weeks of this course. In week 1, we'll go over neural networks and how to carry out inference or prediction. So if you were to go to the internet and download the parameters of a neural network that someone else had trained and whose parameters they had posted on the internet, then to use that neural network to make predictions would be called inference. And you learn how neural networks work and how to do inference in week 1, in this week. Next week, you learn how to train your own neural network. In particular, if you have a training set of labeled examples X and Y, how do you train the parameters of a neural network for yourself? In the third neural networks and how to carry out inference or prediction. So if you were to go to the internet and download the parameters of a neural network that someone else had trained and whose parameters that... Welcome to course 2 of this machine learning specialization. In this course, you learn about neural networks, also called deep learning algorithms, as well as decision trees. These are some of the most powerful and widely used machine learning algorithms, and you get to implement them and get them to work for yourself. One of the things you see also in this course is practical advice on how to build machine learning systems. This part of the material is quite unique to this course. When you're building a practical machine learning system, there are a lot of decisions you have to make, such as should you spend more time collecting data, or should you buy a much bigger GPU to build a much bigger neural network? Even today, when I visit a leading tech company and talk to the team working there on a machine learning application, unfortunately, sometimes I look at what they've been doing for the last 6 months and go, gee, someone could have told you maybe even 6 months ago that that approach wasn't going to work that well. With some of the tips that you learn in this course, I hope that you'll be one of the ones to not waste those 6 months, but instead be Even today, when I visit a leading tech company and talk to the team work, with some of the tips that you learn in this course, I hope that you'll be one of the ones to not waste those 6 months, but instead be able to make more systematic and better decisions about how to build practical working machine learning applications. So with that, let's dive in. In detail, this is what you see in the 4 weeks of this course. In week 1, we'll go over neural networks and how to carry out inference or prediction. So if you were to go to the internet and download the parameters of a neural network that someone else had trained and whose parameters they had posted on the internet, then to use that neural network to make predictions would be called inference. And you learn how neural networks work and how to do inference in week 1, in this week. Next week, you learn how to train your own neural network. In particular, if you have a training set of labeled examples X and Y, how do you train the parameters of a neural network for yourself? In the 3rd week, we'll then go into practical advice for building machine learning systems. And I'll share with you some tips that I think even highly paid engineers building machine learning systems very successfully today don't really always manage to consistently apply. And I think that will help you build systems yourself efficiently and quickly. And then in the final week of this course, you learn about decision trees. While decision trees don't get as much buzz in the media, there's a little bit less hype about decision trees compared to neural networks. They are also one of the widely used and very powerful learning algorithms that I think there's a good chance you end up using yourself if you end up building an application. So with that, let's jump into neural networks. And we're going to start by taking a quick look at how the human brain, that is, how the biological brain works. Let's go on to the next video. When neural networks were first invented many decades ago, the original motivation was to write software that could mimic how the human brain or how the biological brain learns and thinks. And even though today neural networks, sometimes also called artificial neural networks, have become very different than how any of us might think about how the brain actually works and learns, some of the biological motivation still remains in the way we think about artificial neural networks or computer neural networks today. So let's start by taking a look at how the brain works and how that relates to neural networks. The human brain, or maybe more generally the biological brain, demonstrates a higher level or more capable level of intelligence than anything else we've been able to build so far. And so neural networks has started with the motivation of trying to build software to mimic the brain. Work in neural networks had started back in the 1950s, and then it fell out of favor for a while. Then in the the 1980s and early 1990s, They gained in popularity again and showed tremendous traction in some applications like handwritten digit recognition, which were used even back then to read postal codes for routing mail and for reading dollars figures in handwritten checks. But then it fell out of favor again in the late 1990s. And it was from about 2005 that it enjoyed a resurgence and also became maybe rebranded a little bit with deep learning. One of the things that surprised me back then was deep learning and neural networks meant very similar things. But I maybe underappreciated at the time that the term deep learning just sounds much better because it's deep and it's learning. And so that turned out to be the brand that took off in the last decade or decade and a half. And since then, neural networks have revolutionized application area after application area. I think the first application area that modern neural networks or deep learning had a huge impact on was probably speech recognition, where we started to see much better speech recognition systems due to modern deep learning. And authors such as Li Deng and Jeff Hinton were instrumental to this. And then it started to make inroads into computer vision. And sometimes people still speak of the ImageNet moment in 2012. And that was maybe a bigger splash where it then caught broader imagination and had a big impact on computer vision. Then in the next few years, it made its inroads into text or into natural language processing and so on and so forth. And now neural networks are used in everything from climate change to medical imaging to online advertising to product recommendations, and really lots of application areas of machine learning now use neural networks. Even though today's neural networks have almost nothing to do with how the brain learns, there was the early motivation of trying to build software to mimic the brain. So how does the brain work? Here's a diagram illustrating what neurons in a brain looks like. All of human thought is from neurons like these in your brain and mine, sending electrical impulses and sometimes forming new connections with other neurons. Given a neuron like this one, it has a number of inputs where it receives electrical impulses from other neurons, and then this neuron that I've circled carries out some computations and will then send its output to other neurons via these electrical impulses. And this upper neuron's output in turn becomes the input to this neuron down below, which again aggregates inputs from multiple other neurons to then maybe send its own output to yet other neurons. And this is the stuff of which human thought is made. Here's a simplified diagram of a biological neuron. A neuron comprises a cell body, shown here on the left. And if you have taken a class in biology, you may recognize this to be the nucleus of the neuron. And if you saw them in a biology class, you may remember them, but you don't really need to memorize any of these terms for the purpose of building artificial neural networks. And I'm going to draw a little circle here to denote a single neuron. And what a neuron does is it takes some inputs, one or more inputs, which are just numbers, and it does some computation and it outputs some other number, which then could be an input to a second neuron, shown here on the right. When you're building an artificial neural network or a deep learning algorithm, rather than building one neuron at a time, you often want to simulate many such neurons at the same time. And so when in this diagram, I'm drawing 3 neurons, And what these neurons do collectively is input a few numbers, carry out some computation, and output some other numbers. Now, at this point, I'd like to give one big caveat, which is that even though I made a loose analogy between biological neurons and artificial neurons, I think that today we have almost no idea how the human brain works. In fact, every few years, neuroscientists make some fundamental breakthrough about how the brain works, and I think will continue to do so for the foreseeable future. And that to me is a sign that there are many breakthroughs that are yet to be discovered about how the brain actually works. And thus attempts to blindly mimic what we know of the human brain today, which is frankly very little, probably won't get us that far toward building real intelligence. Certainly not with our current level of knowledge in neuroscience. Having said that, even with these extremely simplified models of a neuron, which we'll talk about, we'll be able to build really powerful deep learning algorithms. And so as you go deeper into neural networks and into deep learning, even though the origins were biologically motivated, don't take the biological motivation too seriously. In fact, those of us that do research in deep learning have shifted away from looking to biological motivation that much, but instead are just using engineering principles to figure out how to build algorithms that are more effective. But I think it might still be fun to speculate and think about how biological neurons work every now and then. The ideas of neural networks have been around for many decades. So a few people have asked me, hey, Andrew, why now? Why is it that only in the last handful of years that neural networks have really taken off? This is a picture I draw for them when I'm asked that question, and that maybe you could draw for others as well if they ask you that question. Let me plot on the horizontal axis the amount of data you have for a problem, and on the vertical axis, the performance or the accuracy of a learning algorithm applied to that problem. Over the last couple decades, with the rise of the internet, the rise of mobile phones, the digitalization of our society, the amount of data we have for a lot of applications has steadily marched to the right. A lot of records that used to be on paper, such as if you order something, rather than it being on a piece of paper, that's much more likely to be a digital record. Your health record, if you see a doctor, is much more likely to be digital now compared to on pieces of paper. And so in many application areas, the amount of digital data has exploded. And what we saw was with traditional machine learning algorithms, such as logistic regression and linear regression, even as you fed those algorithms more data, it was very difficult to get the performance to keep on going up. So it was as if the traditional learning algorithms like linear regression and logistic regression, they just weren't able to scale with the amount of data we could now feed it, and they weren't able to take effective advantage of all this data we had for different applications. And what AI researchers started to observe was that if you were to train a small neural network on this data set, then the performance maybe looks like this. And if you were to train a medium-sized neural network, meaning one with more neurons in it, its performance may look like that. And if you were to train a very large neural network, meaning one with a lot of these artificial neurons, then for some applications, the performance would just keep on going up. And so this meant two things. It meant that for a certain class of applications where you do have a lot of data, sometimes you hear the term big data tossed around. If you're able to train a very large neural network to take advantage of that huge amount of data you have, then you could obtain performance on anything ranging from speech recognition to image recognition to natural language processing applications and many more that just were not possible with earlier generations of learning algorithms. And this caused deep learning algorithms to take off. And this too is why faster computer processors, including the rise of GPUs or graphics processor units, this is hardware originally designed to generate nice looking computer graphics, but turned out to be really powerful for deep learning as well. That was also a major force in allowing deep learning algorithms to become what it is today. That's how neural networks got started, as well as why they took off so quickly in the last several years. Let's now dive more deeply into the details of how a neural network actually works. Please go on to the next video. To illustrate how neural networks work, let's start with an example. We'll use an example from demand prediction in which you look at a product and try to predict, will this product be a top seller or not? Let's take a look. In this example, you're selling t-shirts and you would like to know if a particular t-shirt will be a top seller, yes or no. And you have collected data of different t-shirts that were sold at different prices, as well as which ones became a top seller. This type of application is used by retailers today in order to plan better inventory levels as well as marketing campaigns. If you know what's likely to be a top seller, you would plan, for example, to just purchase more of that stock in advance. So in this example, the input feature X is the price of the t-shirt. And so that's the input to the learning algorithm. And if you apply logistic regression to fit a sigmoid function to the data that might look like that, then the output of your prediction might look like this, 1/1 plus e to the negative wx plus b. Previously, we had written this as f of x as the output of the learning algorithm. In order to set us up to build a neural network, I'm going to switch the terminology a little bit and use the alphabet A A to denote the output of this logistic regression algorithm. The term A stands for activation, and is actually a term from neuroscience, and it refers to how much a neuron is sending a high output to other neurons downstream from it. It turns out that this logistic regression unit, or this little logistic regression algorithm, can be thought of as a very simplified model of a single neuron in the brain, where what the neuron does is it takes as input the price X, and then it computes this formula on top, and it outputs the number A, which is computed via this formula, and it outputs the probability of this t-shirt being a top seller. Another way to think of a neuron is as a tiny little computer whose only job is to input one number or a few numbers, such as a price, and then to output one number or maybe a few other numbers, which in this case is the probability of the t-shirt being a top seller. And as I alluded in the previous video, a logistic regression algorithm is much simpler than what any biological neuron in your brain or mine does, which is why the artificial neural network is such a vastly oversimplified model of the human brain, even though in practice, as you know, deep learning algorithms do work very well. Given this description of a single neuron, building a neural network now just requires taking a bunch of these neurons and wiring them together or putting them together. Let's now look at a more complex example of demand prediction. In this example, we're going to have 4 features to predict whether or not a t-shirt is a top seller. The features are the price of the t-shirt, the shipping costs, the amount of marketing of that particular t-shirt, as well as the material quality. Is this a high quality thick cotton, or is this maybe a lower quality material? Now, you might suspect that whether or not a t-shirt becomes a top seller actually depends on a few factors. First, what is the affordability of this t-shirt? Second is, what's the degree of awareness of this t-shirt that potential buyers have? And third is perceived quality. Do buyers or potential buyers think this is a high quality t-shirt? And so what I'm going to do is create one artificial neuron to try to estimate the probability that this t-shirt is perceived as highly affordable. And affordability is mainly a function of price and shipping costs, because the total amount you have to pay is the sum of the price plus the shipping costs. And so we're going to use a little neuron here, a logistic regression unit, to input price and shipping costs and predict, do people think this is affordable? Second, I'm going to create another artificial neuron here to estimate, is there high awareness of this? And awareness in this case is mainly a function of the marketing of the t-shirt. And finally, going to create another neuron to estimate, do people perceive this to be of high quality? And that may mainly be a function of the price of the t-shirt and of the material quality. Price is a factor here because fortunately or unfortunately, if there's a very high priced t-shirt, people will sometimes perceive that to be of high quality, because if it's very expensive, then maybe people think it's got to be of high quality. Given these estimates of affordability, awareness, and perceived quality, we then wire the outputs of these 3 neurons to another neuron here on the right, that then is another logistic regression unit that finally inputs those 3 numbers and outputs the probability of this t-shirt being a top seller. So in the terminology of neural networks, we're going to group these 3 neurons together into what's called a layer. And a layer is a grouping of neurons which take as input the same or similar features, and that in turn output a few numbers together. So these 3 neurons on the left form one layer, which is why I drew them on top of each other. And the single neuron on the right is also one layer. The layer on the left has 3 neurons, so a layer can have multiple neurons, or it can also have a single neuron, as in the case of this layer on the right. This layer on the right is also called the output layer, because the output of this final neuron is the output probability predicted by the neural network. In the terminology of neural networks, we're also going to call affordability, awareness, and perceived quality to be activations. The term activations comes from biological neurons, and it refers to the degree that a biological neuron is sending a high output value or sending many electrical impulses to other neurons that are downstream from it. And so these numbers on affordability, awareness, and perceived quality are the activations of these three neurons in this layer. And also, this output probability is the activation of this neuron shown here on the right. So this particular neural network, therefore, carries out computations as follows. It inputs 4 numbers. Then this layer of the neural network uses those 4 numbers to compute 3 new numbers, also called activation values. And then the final layer, the output layer of the neural network, uses those 3 numbers to compute 1 number. And in a neural network, this list of 4 numbers is also called the input layer. And that's just a list of 4 numbers. Now, there's one simplification I'd like to make to this neural network, which is the way I've described it so far, we had to go through the neurons one at a time and decide what inputs it would take from the previous layer. So for example, we said affordability is a function of just price and shipping costs, and awareness is a function of just marketing and so on. But if you're building a large neural network, it'd be a lot of work to go through and manually decide which neurons should take which features as inputs. The way a neural network is implemented in practice, each neuron in a certain layer, say this layer in the middle, will have access to every feature, to every value from the previous layer, from the input layer, which is why I'm now drawing arrows from every input feature to every one of these neurons shown here in the middle. And you can imagine that if you're trying to predict affordability and it knows what's the price, shipping cost, marketing, and material, maybe it'll learn to ignore marketing and material and just figure out through setting the parameters appropriately to only focus on the subset of features that are most relevant to affordability. To further simplify the notation and the description of this neural network, I'm going to take these 4 input features and write them as a vector X. And we're going to view the neural network as having 4 features that comprise this feature vector X. And this feature vector is fed to this layer in the middle, which then computes 3 activation values. That is these 3 numbers. And these 3 activation values, in turn, becomes another vector, which is fed to this final output layer that finally outputs the probability of this t-shirt being a top seller. So that's all a neural network is. It has a few layers where each layer inputs a vector and outputs another vector of numbers, where, for example, this layer in the middle inputs 4 numbers, X, and outputs 3 numbers corresponding to affordability, awareness, and perceived quality. To add a little bit more terminology, you've seen that this layer is called the output layer, and this layer is called the input layer. To give the layer in the middle a name as well, this layer in the middle is called a hidden layer. I know that this is maybe not the best or the most intuitive name, but that terminology comes from that when you have a training set, in the training set, you get to observe both X and Y. Your data set tells you what is X and what is Y. And so you get data that tells you what are the correct inputs and the correct outputs, but your data set doesn't tell you what are the correct values for affordability, awareness, and perceived quality. And so the correct values for those are hidden. You don't see them in a training set, which is why this layer in the middle is called a hidden layer. I'd like to share with you another way of thinking about neural networks that I found useful for building my intuition about it. Just let me cover up the left half of this diagram and see what we're left with. What you see here is that there is a logistic regression algorithm or a logistic regression unit that is taking as input affordability, awareness, and perceived quality of a t-shirt and using these 3 features to estimate the probability of the t-shirt being a top seller. So this is just logistic regression. But the cool thing about this is, rather than using the original features, price, shipping cost, marketing, and so on, is using a new, maybe better set of features, affordability, awareness, and perceived quality, that are hopefully more predictive of whether or not this t-shirt will be a top seller. So one way to think of this neural network is just logistic regression. But it is a version of logistic regression that can learn its own features that makes it easier to make accurate predictions. In fact, you might remember from the previous course, this housing example where we said that if you want to predict the price of a house, you might take the frontage or the width of a lot and multiply that by the depth of a lot to construct a more complex feature, x1 times x2, which was the size of the lot. So there we were doing manual feature engineering where we had to look at the features x1 and x2 and decide by hand how to combine them together to come up with better features. What a neural network does is instead of you needing to manually engineer the features, it can learn, as you see later, its own features to make the learning problem easier for itself. So this is what makes neural networks one of the most powerful learning algorithms in the world today. So to summarize, a neural network does this. The input layer has a vector of features, 4 numbers in this example. It is input to the hidden layer, which outputs 3 numbers. And I'm going to use a vector to denote this vector of activations that this hidden layer outputs. And then the output layer takes as input those 3 numbers and outputs 1 number, which would be the final activation or the final prediction of the neural network. One note, even though I previously described this neural network as computing affordability, awareness, and perceived quality, one of the really nice properties of a neural network is when you train it from data, you don't need to go in to explicitly decide what are the features, such as affordability and so on, that the neural network should compute. Instead, it will figure out all by itself what are the features it wants to use in this hidden layer. And that's what makes it such a powerful learning algorithm. So you've seen here one example of a neural network, and this neural network has a single layer that is a hidden layer. Let's take a look at some other examples of neural networks, specifically examples with more than one hidden layer. Here's an example. This neural network has an input feature vector x that is fed to one hidden layer, and I'm going to call this the first hidden layer. And so if this hidden layer has 3 neurons, it will then output a vector of 3 activation values. These 3 numbers can then be input to a second hidden layer. And if this second hidden layer has 2 neurons, 2 logistic units, then this second hidden layer will output another vector of now 2 activation values that maybe goes to the output layer that then outputs the neural network's final prediction. Or here's another example. Here's a neural network that has its input goes to the first hidden layer, that the output to the first hidden layer goes to the second hidden layer, goes to the third hidden layer, and then finally to the output layer. When you're building your own neural network, one of the decisions you need to make is how many hidden layers do you want and how many neurons do you want each hidden layer to have? And this question then this second hidden layer will output another vector of now 2 activation values that maybe goes to the output layer that then outputs the neural network's final prediction. Or here's another example. Here's a neural network that has its input goes to the first hidden layer, that the output of the first hidden layer goes to the second hidden layer, goes to the third hidden layer, and then finally to the output layer. When you're building your own neural network, one of the decisions you need to make is how many hidden layers do you want and how many neurons do you want each hidden layer to have? And this question of how many hidden layers and how many neurons per hidden layer is a question of the architecture of the neural network. You learn later in this course some tips for choosing an appropriate architecture for a neural network. But choosing the right number of hidden layers and number of hidden units per layer can have an impact on the performance of your learning algorithm as well. So later in this course, you learn how to choose a good architecture for your neural network as well. Oh, and by the way, in some of the literature, you see this type of neural network with multiple layers like this called a multi-layer perceptron. So if you see that, that just refers to a neural network that looks like what you're seeing here on the slide. So that's a neural network. I know we went through a lot in this video, so thank you for sticking with me, but you now know how a neural network works. In the next video, let's take a look at how these ideas can be applied to other applications as well. In particular, we'll take a look at the computer vision application of face recognition. Let's go on to the next video.